which is like totally awesome.
Let's try that again. I'm Brad Nelson, doer of various fourthy things. Today I'm going to be talking about bringing Lisp-style abstraction to Forth. This is kind of a follow-on to a talk that I gave over a year ago, where I went through the Structured Interpretation of Computer Programs textbook from an old MIT course, and sort of looked at how to bring each of those the ideas in that book, or at least a substantial subset of that book, to Forth. One of the places where I left things off for detail's sake was looking at how you might do garbage collection. I basically just leaked memory like crazy and focused just on abstraction. This time I'm going to go back and look at how you might bring a garbage collector to Forth. Basically what I'm going to do is go through and talk about how Lisp represents data, at least in the sort of the classic core of Lisp, and look at how it is sort of a closed means of combination, and then how you would go about building a GC in Forth that can work with that, and then look at some of the cool things that you can do, especially when you've got the garbage collection right. When I looked at this before, I was just accumulating data into the heap without bound, and so you had to be kind of careful to not overflow the heap. When you actually do collection, you can do all kinds of fun things. One thing that fell out of me looking at this was a realization that I could change the way I had done binding differently from what I had done before, and we'll talk about that as well. So in a classic Lisp, the sort of core data structure is a pair, two items, a car and a cutter, and the basic rules are this: if you have use a cons, you can take two elements, combine them into a thing, a pair, and then the car of that element is the first one, and the cutter is the second one, and everything sort of any substance is built up out of these. There's a representation for data in this form that is a little more human readable. If you have two elements and you cons them together, you get what's called a dotted pair that's represented between parens with a dot like this. And most importantly, if you have a chain of conses where you successively attach a new car on the front of the chain, you build up a list, and this is canonically how you would internally represent a list. So what this looks like in the machine's memory is that you have a bunch of these pairs, and then they have pointers to each other, and then at the end you have a marker for nil. You can have a dotted pair in combination if it happens to fall at the end. There's a sort of a notation for representing that. But the key thing is that you're building up everything out of these two element structures, and you're able to. There are a lot of things that are allowed that sort of make this more flexible than it would first seem. One is that you are allowed to have cycles. So you're allowed, for example, to have structures that loop back on themselves. Oops. But commonly, the way that you would use this to represent interesting things is, like, for example, say you had a mapping from one kind of a value to another, you might have a series of pairs, a list of pairs, and store it that way. There are obviously some efficiency considerations. If you were, there are cases where this kind of structure will be inefficient if you're trying to build up something that you want direct indexing into. You end up having to sometimes do something order n that in an array would be more efficient. You would be able to just go to the particular element, but these are sort of details. And the nice thing about this is that it is a closed means of abstraction. It offers the idea that everything is of this type. You can build pairs of pairs ad infinitum, and it's sort of fun and flexible. So to represent this in Forth, what I've what I've done is I've got two words, pair and unpair. Pair takes two elements off the stack and binds them together into a pair. And then unpair will unpair them, separate them back out. I also have car and cutter, which just pull out a single item. Car and cutter are these obscure names due to the sort of weird history of the first machine that Lisp was implemented on, for those wondering. But to make this, so, and as those of you who caught my prior talk, there's all kinds of interesting things. We'll talk about a subset of them that you can do with this in a moment, but let's talk about how you would implement this. One challenge, of course, is that if you start willy-nilly just pairing these things up, you have a problem where now you're potentially leaking memory, because if you had to have memory to store these two elements, it may not be clear which of them you're done with. If you drop one off, if you say pair two items and then drop this pair off of the stack, you need to have the machine keep track of when to recover that. And traditionally, because you're allowed to have cycles, you want to avoid having to have this be something that's manually done. Instead, you want to have the machine look for the garbage, as it were. I see a question in the chat. Is that a question in the chat? I don't see that. Okay. See the chat right now. All right, yeah, ask your question out loud. I won't mind if you interrupt me. There are two broad categories of garbage collection that are sort of done: mark and sweep and stop and copy. And the idea, the sort of broad distinction is that mark and sweep, you tend to leave the things that are not garbage alone, and you try to sort of figure out which of them they are and recover the items that are garbage. Stop and copy, you go and you copy off everything that is not garbage into a new area, and thereby sort of assume that everything else is garbage. In a sort of commercial large-scale garbage collector, as you might find in the JVM or in a JavaScript engine, you typically combine these strategies, and there are all kinds of hybrids, and this is an elaborate body of, to some degree, even active research around how you might do this better and well. Typically, what you end up wanting to do is to have multiple pools of memory, where you will, for example, use a stop and copy strategy for a smaller pool of newer, more recent objects, and then maybe use a mark and sweep strategy for larger objects or longer-lived objects. And there's all kinds of variations here. An interesting variation on this one I touched on long ago is a type of collector called a Boehm collector, Hans Boehm, who I've met actually. His strategy, it's basically what's called a conservative collector, where imagine that you have objects where you haven't been particularly careful about distinguishing which items are part of your heap and which are sort of other types of data structures. The idea is that basically you make a conservative assumption that if it looks like it might be something that is a reference, you assume that it is. And this opens up the possibility of doing a collector for a language that isn't type safe. For example, you can do garbage collection on top of that. The collector I'm going to present here is, interestingly, I originally intended to do a mark and sweep collector, but I've actually ended up doing a stop and copy collector, and I'll talk about sort of some fascinating things that fell out of that. Oops, that's the wrong button. So stop and copy is this idea from Cheney in 1970, and it's wasteful in one critical fashion. It requires you to have double the memory that you're going to actually use. You have what's called a from and a to space, and every time you run out of memory in one of these spaces, what you do is you copy all of the live objects over from the old space into the new space, and then you toggle which one is which. And because you may have, almost all of the from space might be full of non-garbage, in the limit you need to have approximately the same amount of memory. So you end up having to partition your memory into two halves and to bucket bail from one to the other. This might not be so one sort of counterintuitive positive benefit of this is that on modern CPUs, the act of copying everything over and packing them tightly actually can have a caching benefit, because now you've brought all of the live objects in proximity to each other, and so they're oftentimes sort of adjacent in a way that if they were sprinkled through memory would actually be less efficient. there's one crucial thing to this is the trick of leaving what's called a broken heart to bind the element, to link from elements in the old space to the new space as you're doing this. And I'll walk you through how that works. So I'm going to switch over to a different view and sort of outline this. So imagine that you're trying to build up, you've got a data structure that looks something like this, where let's say we've got a 1 and a 2 and a 3. And just to make it fun, let's imagine that these are each in the cars, the first element. Let's imagine that the cutters link this into a ring. And then let's say this one loops around back. So they're sort of, this forms a cycle. And let's say that you reached the point where you needed to figure out which objects are live, and let's pretend that you actually have some root reference to this object. And then say in memory, these were laid out like this. Maybe there's some piece of garbage here. And then got this guy, and this guy here. And so this is what's in your old space, and because you've now filled it up, you need to go and move over the live objects into the new space. And in your new space, you're going to need sort of two things. You're going to need a high water mark for how much you've allocated, and then you're going to need a marker for how many you've kind of resolved the references on. Mark that in green. And to be clear, these still have all of their links to each other. You know, this guy points to this guy, number 2 points to number 3, and number 3 points back to number 1. And so what you do in a Cheney collector is you start at your root, and we've got this guy as the one root, and you bring him over into the new space because he's a root, so he obviously needs to come along. And when you do that, you need to mark him with what's called a broken heart. I guess I could do a heart there, where you mark him as undone, and then you change his cutter to point to the spot in the new space. But because you've made a copy of him, this guy still has a reference, to number 2 here. You then, because you've allocated space, you now move your high watermark along, and then you're ready to proceed. And one critical thing about this is that because you're all of the memory that you need is sort of here, and so there's no recursion. You're not building up extra stuff on the stack. You're able to do this actually with basically just a handful of pointers in the memory here. So you need to move this guy along, and the idea is eventually you're going to reach a point where the screen and the white sort of meet for good, and they've converged, and that's when you know you're done. But at this point, you look at this element, and you say, oh, he's got some outbound references into the old space, so you know you're not done. So you look at who he references, and you say, oh, we've got to copy him over into this area, and you bring him over, and he, in the same way, right, you're copying it verbatim, so he has a link over to number 3 here. And in the same way, you need to mark him with a broken heart, and then have him reference his new space version. And you've allocated space, so this guy moves up, and then you're ready to process. And I should be clear, like, the reason for these 2 pointers is that imagine something that's a tree. You would end up accumulating the white one would get well ahead of the green one, and so you could have a pile of yet to be processed elements that the green one needs to catch up to. But in this particular example, you're only ever one behind. So you move him along, and now you examine this guy, and he has a reference to 3, which is also in the new space. So you now need to bring him over, and he looks like that. And then similarly, but an interesting thing happens at this point, which is when you go to copy him over, you look and you say, okay, well, he has a reference over to this red one, but this red one is now a broken heart pointing back here, and that's your cue to to know that instead of copying him verbatim linked to that broken heart, at this point, you can take the opportunity to link back to what the broken heart points to. And oh, yeah, sorry, one other detail I forgot to mention. As you're bringing in each of these references, you needed to because you need to hook them to point to the appropriate local copy at that point. And then similarly, this guy gets his broken heart, and that's just pro forma, and then he points over here. And because you've now moved these along, these two are here, and you're done. So that's how you recover. That's how you recover space. You can do this in a fairly small amount of forth code. I'm just going to show you the overall shape of it, and we'll look at it in a little more detail. But basically, allocation is really straightforward. You just allocate a bunch of space on the conventional fourth heap. Have a couple of pointers, this pair break and pair base, to keep track of where you're at. The base is so that you know which of the two spaces you're in. And then car and cutter are really straightforward, right? You're just two elements. The P is just a, the pair is just a pointer to the element, and you get either the first element or the second element. I should have mentioned that in sort of a more general formulation of all of this in Lisp, you're allowed to modify the car and the cutter. And then you need a little bit of plumbing to know whether something is a pair, whether it's in the old space or not. And then how does collection work? Well, we're going to defer the actual collection, and then we'll need this special word for null and a word to check for nil and those sorts of things. And then we just need to measure if the pair break has reached the capacity of one of these two, the old space or the new space. And every time we try to reserve memory, if things are full, then we do a garbage collect. The way we allocate, we'll build up a word to just produce a new pair and to populate that to move along the pair break by one cell, and that lets us create one pair by reserving space for it, allocating the pair, and then storing the car and the cutter into the pair. We can also call this cons because that's the sort of more conventional Lisp-y name, but for symmetry, I like having a word unpair and unpair. And unpair just does the car and the cutter and gets them back out. So that's just the allocation. And now if we want to do, we'll need to have some roots to be able to do this collection. And I've got one variable to keep track of a chain of roots. And I've actually got this defining word. I'm using value here to create a root so that you can do something like nil root foo, and now foo is a root that will stay alive. And if you stored something into foo, if you had some list and you said to foo, that will because it's been labeled as a root, it will keep it alive. If you did this into just a normal variable, the garbage collector doesn't know about it, and so it will lose it. And then the actual collect, you need to have a marker for a broken heart, and you can pick an arbitrary marker, so just some variable, it doesn't matter, you're just using the address of it. And then you need to be able to relocate individual items, and then you need to basically go and check if you need to do further relocations if you happen to want to catch up that green pointer, and then you go through and do the fix-ups as you go. And then you need to walk three different things. You need to walk those roots that we talked about before that are sort of explicit variables. And then you need to walk both the data stack and the return stack, because you might have things there. And a critical thing throughout this is that you're assuming that if you see a value on the stack, if it is inside of that heap space, you assume that it's a reference to that pair. So it's being conservative, kind of like a Boehm collector, although a Boehm collector traditionally leaves memory in place, which has some good properties because it lets you have references to things that you've dynamically allocated with malloc or things of that sort. But it ended up being interesting to have this be dynamic. And then there's a little bit of plumbing to swap the new space and the old space, and to pick which heap you're on. And then the collect this is just the high level collect. You toggle which space you're in, you rock the roots, you said the return stack, the data stack, all the roots, you catch up that green pointer, and then if by some unfortunate chance the heap is still full after this, then you throw an error because you're out of space if you can't collect it. So this assumes a fixed size overall heap. There's a little bit of plumbing for now that you have all of this, you can do some things to make it more ergonomic. So I've got this L print word that goes through and recursively prints in Lisp style parens. And I've also got a different version of a word that takes multiple items off the stack and turns them into a pair. So you can do 9, 8, 7, and because there's 3 items, you say this is a list, and if you print that, you get a 3-element list. You can also build up these, use double parens. It's good suggestions here would be good. I didn't want to override comments for this, but so I ended up using double parens to mean what a single paren would mean. And just for symmetry, I used a double dot for the dot. And so I've got this notation will let you input a list like this. And if you go to print it, you get sort of proper list pairs, and you can nest them and list pairs like this. So let's see, how are we doing on time? That took, oh, sorry, I'm well over time, so I'm going to speed along here. And very fascinating thing you can do is add to this the idea of binding arguments to procedures. The idea is that instead of doing you can build a multiplier operation with create does, but instead of doing it that way, you can use these bind and invoke. So the idea is bind and invoke are a pair. Bind lets you bind an execution token to one or more elements by just putting them into a pair, and invoke will unwrap those and put them on the stack. And so you can do this multiplier a different way by saying, let me take the multiply operation and bind it to the element that's passed in. So if you bind 3, you create a multiplier bound to 3, you can then invoke it, and then it'll apply to 7. And you can do multiple of these. You can bind several elements to this, to say a word foo. And when you run, now if you invoke the thing that's returned by this expression, you can then execute it. So this lets you do a bunch of cool things. I won't go into the details here, but you can build up a for each operation. And this for each operation will take a list and it will take a list and a list and an operation, which is something to invoke, and we'll invoke that operation on each element of the list. So for example, you can create a summation by starting out with 0, swapping that around to get your list out from underneath, and then doing a for each on it where you do add, and that goes down the list, adding to the sum. And then you can sum a list in this way. You can build up chaining so that if you have 2 operations, like say you want to chain together 1 plus and square, you can chain that as to become a single operation that you can invoke. So you could sort of build things up without defining any words. And this lets you kind of recursively do things like here. This is binding together 2 with multiply. You get 2 times. And similarly binding 1 with plus, and then chaining those 2 together so that you get a 2 times and a 1 plus, and you can invoke those as a single operation. Using all of this, you can do some fun things. You can take a list and you could build up a length operation by chaining together a drop and a plus, and that will count up the items in the list. You can also build up an average operation by then using our previous sum and length operation. You can do things like that, get the length of the list or the average of the list. I found it convenient to have a way to swap pairs of, to do a swap and then pair so that you get sort of a car and a cutter in the opposite order. And then you could use this to, for example, build up reverse append that appends B reversed to A. And then using this, you can easily build reverse, which just reverses a list. So if you give it 1, 2, 3, 4, you get out 4, 3, 2, 1. And note that that could be an arbitrarily nested list. You can build append and be able to take two lists and append them together. Oops. And you can build map, which has a list of items and applies an operation to it. So like here, we're squaring each element in the list. You can build a range operation to create a list that covers a certain range. So from 0 up to 10, and out you get your range. You can build a filter operation that lets you filter all the elements in a list to filter them out. So if you had the range of numbers from 2 to 100, and you filter just the ones that satisfy the prime test, out comes the primes. This will be useful later. You can build up and check for recursive equality. There's a bunch of caveats to this. Because I'm assuming that numbers I'm assuming that if something looks like a pair, it is a pair. If you have a number that's in the range of the pointers in the heap, this will be unstable. So what this means is that you need to either build your lists out of numbers that are small enough that you know that they won't collide with the heap space, or you need to augment the approach with boxing or other approaches, or you need to use elements that are pointers to other parts of the heap, so you're confident that they're not there. Like you could use just random regular fourth variables as atoms. There's a bunch of things you can do around concurrency and performance. I'm going to leave this yet again for another time. The slide deck has an interesting set of things to it, but are there questions? And apologies for going over. Someday I'll talk about the slide deck tool.
Brad, just as noting by there.
Yes.
Brad, oh, yeah, Brad?
Yes, I can hear you.
It's almost like you gave an introduction to a hell of a lot of, Cozy, because I just made a note that Arthur Whitney once made a comment that K was sort of like a list with n item lists instead of 2 item lists. And so there's a tremendous amount of similarity between, I've noted some things where essentially the verb in Cozy's the equivalent to your pair and unpair, for instance. But one of the other things is I had a conversation next to an elevator, waiting for an elevator with Arthur, where he had made a comment that he never moved anything in memory. And so in garbage collection, and it's reference counted. And when you have such a structure, such a crystalline structure as lists and lists of lists, then you should be able to keep your accounting as it goes on. When I was out there a couple of years ago, I happened to be introduced to Ken Thompson at the Bean Scene. We chatted for about an hour, I guess, but one of the things is he was contending that reference counting was old hat. And I was wishing that Arthur was there to go and argue the case. But the thing is, Arthur's system is essentially you just have a inventory of power of 2 length slots, starting with some low end. And I should probably give a talk sometime on the reference counting in Cozy, because that is the real hurdle. To have dynamic objects is the real hurdle between the fourth level of things and the human level of things. Having arbitrary dynamic objects. But in any case, the reference stuff you'll see is very similar. But I'll tell you, Yeah, the idea of never moving anything. I've not totally implemented that, but the algebra of reference counting, I'd call it that, the reference vocabulary is just absolutely the center of everything. And Sam Falvo, in his talk, he went right to the center of it when he talked about how when you delete an object, you recursively delete you decrement the reference counts, and when they go to zero, when they return to zero, you free them.
I think one of the interesting things, I mean, so reference counting as a mechanism, I think in general is has the benefit of being simple and straightforward. One of the challenges with applying it to sort of Lisp-y structures is exactly because Lisp allows cycles. Now, the weird thing is that most of where you actually get cycles in Lisp come from situations where you're using it with those bindings and with closures and things of that sort. And the vast majority of the time you don't have cycles. And if you can avoid cycles, then you can use reference counting. The challenge with reference counting is that it doesn't fully generalize if you need to collect cycles. The odd bit though is that most of the interesting things you don't need to collect the cycles. You don't, if you're, as long as you sort of haven't built sort of everything upon having those cycles, then there are a lot of cases where you can avoid it. And in a lot of contemporary languages, they go one step further. They try to, in Rust, for example, they try to avoid situations where you're not able to understand at compile time sort of the allocation order. So you're essentially doing what amounts to what would be the bookkeeping for reference counting, but at compile time, and sort of constraining how your program has to be shaped in order to meet those constraints. So there's, yeah.
Break. Bob, do you know about how long ago that Sam Falvo talk was?
Oh, I've got a link on it on my cozy/cozy page. There's a link to, so yeah. But
so it's a YouTube video and you've got a link to it. Okay, great. Let's move on. Joseph O'Connor, are you on deck?
Yes, I am. Can you hear me?
I can hear you just fine. You're on.
Thank you. Okay, I'm going to share my screen.
While he's doing that, I'd like to thank everybody who's here for being here, and I'd like to thank the presenters for braving the vagaries of Zoom. Your screen is shared.
Okay,
You're off.
sorry. Okay.